So let's continue this afternoon's program with our next speaker, Dmitry Zaporozhets from the St. Petersburg Department of Steklov Institute. And he'll be talking about approximations of sums of random vectors by infinitely divisible distributions. Please, Dima.
Okay, thank you, Friedrich, for the introduction. And first of all, I, of course, would like to thank the organizer for giving me an opportunity to give a talk here. It is a big honor for me to participate. And today I will speak about some topic which is a little bit new for me, but I think it fits this conference much more than my other interests. So I'll speak about joint result with Friedrich Goetze, who just introduced me, and Andrei Zaitsev. Unfortunately, he couldn't participate because now he is in Bielefeld visiting Friedrich. Okay, and let me begin. The main object is, let us fix some n, natural, and I will speak about non-asymptotic results, so it's convenient to think that n is fixed. And consider random variables xi1, xin from R1. And all I assume is that they are independent. And I even do not assume that they are identically distributed. And it is a well-known result due to Kolmogorov in 1956. Roughly speaking, he showed that the sum of these independent random variables, in some sense, it is close to infinitely divisible class of the infinitely divisible distributions. To be more precise, let me first recall you some notations. First of all, for a random variable xi, denoted by q and some tau, positive tau, denoted by q, xi tau, the concentration function of xi given by the following. It is supremum of all real x of the probability that xi lies in the interval x plus tau. It is well known Levy concentration function. And also, of course, all of you know it, but let me anyway recall the Levy metric for random variables xi prime, the Levy distance between xi and xi prime is defined by infimum over all positive lambda, such that the following relation between the distribution functions of xi and xi primes holds. First of all, the probability that xi is not greater than x is at most the same probability, not the same, sorry. Xi prime is not greater than x plus lambda and plus lambda. And vice versa, the same xi prime here, xi here. Let me do like this. And that is for all real x. That is the classical Levy distance. And let us denote by pi j. Okay, j is from 1 to n. Pi j, it is just 1 minus q of psi j tau. It is the infimum of the probability that psi j does not hit the interval of the length tau. And p is just the maximum among all p1 and so on pn. Okay, that is essentially all notations we need. Okay, and Kolmogorov in 1956, he proved the following thing. And the last notation is, let us denote by capital D. It is a class of all infinitely divisible random variables. Infinitely divisible random variables. Okay, and as I said, he showed that the sum in some sense close to this class. What does it mean? It means that for some absolute constant C, the following inequality holds. Infimum over all eta from this class, over all infinitely divisible eta, of the Levy distance. Oh, sorry, why I put it here like this? It's just L. Levy distance, the Levy distance. Levy distance between the sum, psi1 plus psi n, and eta. In fact, it is just the distance between the sum and the infinitely divisible class D. It is at most this absolute constant C, and p to the power 1 over 5, 1/5, plus tau to the power 1/2, and absolute value of log tau to the power 1/4 plus 1. Kolmogorov actually formulated this result in slightly different form, but for us it is convenient to, and also not for all tau, but for us it's convenient to state it like this result. And it was in this paper which Albert Nikolaev mentioned today after Friedrich's talk, where he cited Prokhorov, and actually he proved two theorems. And yes, sorry. It's no n actually. For any fixed n, it does not depend on n. It depends only on this p. Yeah, in some sense, p depends on n. Yeah. And okay, actually, it was the second theorem, and from this paper, and the first, maybe it is more famous, and maybe it was saying some words about it because it is connected with the activity of Yuri Vasilievich Prokhorov. The first theorem was about identically distributed random variables, and he showed that in this case it is at most C and n to the power minus 1 over 5. It was his result, but actually the first who considered this setup was Prokhorov 1 year before in 1995. 1955. It was a paper in Doklady of Soviet Academy of Sciences. He proved that this quantity goes to zero. And then Kolmogorov decided to prove that actually it is uniform, the convergence is uniform, and he obtains this bound. And okay, few more words about this IID case. Later, again, Prokhorov obtains the estimate 1n to the power minus 1/3 and log n plus 1 to the power 2, this estimate in IID case. And later, it was a paper by Ildar Abluevich Ibragimov and Ernst Lvovich Pressman, where they showed that it is possible to use compound Poisson approximation here. It is possible to take, instead of eta, accompanying Poisson approximation and to obtain similar bounds. But optimal bound finally was obtained by Arak, where he showed that the optimal one here is n to the power minus 2/3. It was obtained by Arak as a final result. It is IID case, but my talk about non-IID case. And it also may be useful to mention that the technique which was, the methods which was used in Kolmogorov paper, in this Kolmogorov paper, who also, as Albert Nikolaevich said, that he used Prokhorov's methods, and these methods, along with the Sperner combinatorial lemma, later was used by Rogozin, who proved the following inequality. Q, consideration function of the sum under the same condition, just independent random variables, no more assumptions, plus psi n is at most some absolute constant over square root of p1 plus pn, or square. Oh, no, it's not square, sorry. Just, yeah. It is very famous Kolmogorov-Rogozin inequality. Now it is known as Kolmogorov-Rogozin inequality. Okay. And later, this bounds, the right bounds was improved by several mathematicians. First of all, by Kolmogorov himself. About 6 years later, he put here 1/13 instead of 1/5. Again by Ibragimov and Pressman. And finally, the optimal bound was obtained in 1984 again by Arak, and also jointly with Andrei Zaitsev. And they showed that under the same assumptions, the right bound is where we have no exponents here. So they proved the following inequality. Okay, and now let us notice that this setup can be naturally extended into higher dimensions. But first of all, sorry, I forgot to mention another result of Arak and Zaitsev in this paper. Besides this inequality, they also considered the Prokhorov-Levy metric. And again, let me recall you what it is. Okay, D, it is infinite dimensional. And Prokhorov-Levy metric, it is Okay, maybe here. Again, for random variables xi prime, it is defined by pi xi prime. It is infimum of positive lambdas such that the probability of xi to be in some Borel set B is at least the probability of xi prime to be inside the lambda neighborhood of B. Lambda neighborhood, it is of course the set of points which are not further from B than lambda. The distance from these points to B is at most lambda. And plus lambda again. And the same vice versa, xi prime is here, xi is here. And it holds for all Borel sets B. So here we consider only half lines, and but here we consider all Borel sets. So in some sense it's stronger. Okay, and they showed that for the Prokhorov-Levy distance, the following inequality holds. Again, here we have infimum over all infinitely divisible distributions. Prokhorov-Levy distance from the sum xi1 plus xin and eta. So it is just the Prokhorov-Levy distance from the sum to the class D, class of the infinitely divisible distributions, random variables. And it is at most almost the same. Here we have the same thing like here, log tau plus 1, but also, because this distance is stronger, also we have some reminder, the sum j from 1 to n, pj square. And in some sense, they showed that it is also optimal, this inequality. So it was their main result in this paper. And later, in 1989, Zaitsev generalized these two inequalities to higher dimensions. And before formulate his result, I again need some notation. First of all, we have to. Okay, maybe I erase this. First of all, we have to generalize the Prokhorov-Levy matrix to higher dimension, but literally the definition stays the same. Nothing changed in high dimensions here. Thus, Borel sets in RD. And the lambda neighborhood, it also well defined in RD, and so on. And our setup is that we have xi1, xin, now they are independent random vectors in RD. Independent. That is our setup. The only assumption is independence. So Levy-Prokhorov matrix is the same. But the situation with the Levy metric is a little bit more subtle. How to generalize it to high dimension. Zaitsev suggested the following generalization. Let us denote by 1D, it is d-dimensional vectors which coordinates are just ones. 1, 1, and so on, 1. And he suggested to consider the following multidimensional definition of the Levy metric. It is the following thing. It is defined by, again, infimum of lambda, such that probability that x is at most x is at most probability that xi prime is at most x plus lambda multiplied by this unit vector plus lambda, and vice versa, xi prime xi, for all x from RD. And having defined this multidimensional Levy metric, Zaitsev proved, let me write this, in 1989, yes, as far as I remember. Zaitsev proved that, let me denote this by this inequality by star, this inequality by 2 star. Zaitsev proved that star and double star hold in RD. That was the main result of Zaitsev. So, in some sense, he generalized these two inequalities to multidimensional case. Okay, but this definition of the multidimensional Levy metric has some disadvantages because it heavily depends on the coordinate system, on the standard basis. While the right hand side here and here, which is composed of the concentration function, and it does not. And sorry, I forgot to define the concentration function in multidimensional case. In multidimensional case, the concentration function of a random vector xi, it is just supremum over all x from RD, the probability that the random vector hits the ball of radius tau centered at x. Maybe it's better to xi minus x is at most tau. Formally, it is a little bit different definition because here the interval of the length tau, so it is a ball of the radius 2 tau, and here the radius is tau. But because everything is up to constants, it doesn't matter for us. So in multidimensional, it's more convenient to consider this, not with tau over 2, but with tau. Okay, and so as I told, this result due to Zaitsev with this definition of the Levy metric is not very natural because this definition depends, it's not coordinate free, while this definition, for example, is coordinate free. So our aim is to suggest a new definition, again stronger than this one, which is coordinate free, and still this inequality, two inequalities hold. And okay, so now I have time to do this, and maybe I need to erase something. Or maybe if I write here, is it okay on the lower half? Okay, first of all, let me introduce some more notations. Let me denote by PM. It is the class of, okay, let me denote it by this. It is the class of all polyhedral sets which are the intersection of M half spaces. So if it is bounded, then it is polytope. If it is unbounded, then it is polyhedral set. So, and let me write it down. What do I mean? It is just, so PM, it is a class of polyhedral sets which can be representative as following. P, it is the set of X from RD such that scalar product of X Tj is at most Bj for some T and Tj and Bj, where the norm of Tj is 1, Bj is just real number, and J is from 1 to M. That is where M comes from. So it is just the intersection of M half spaces. Of course, this representation is not unique for any polyhedral set, but it does not matter for us now. Okay, that is the class PM. And also consider some subclass P star. It is a subclass of PD. What it is? It is the following thing. First of all, let us denote but E1 and so on, En, it's standard orthonormal basis. Standard orthonormal basis in RD. And consider the polyhedral sets which are just the intersection of the half spaces which boundaries are parallel to coordinate planes. Formally, it is just, okay, it is the subclass, or it is the class of P stars, the subclass of PD, and which can be represented as almost the same, but here we have the set of X such that scalar products with our standard basis participate here is at most Bj, where J is from 1 to D. And so for example, our PM, it is just, for example, on the plane P3, it is just the intersection of three hyperplanes. It can be like this, it can be like this. And what is P star in the plane? It is just the intersection of such kind of half spaces. In some sense, it's shifted orthons, just the set of shifted orthons. And okay, and having this definition, the definition given by Zaitsev can be formulated in the equivalent form, it is just, and sorry, before this I need one more notation. And here in the definition of Levy-Prokhorov metric, we have a lambda neighborhood. And now let us introduce some quasi neighborhood. If we have such representation of the polyhedral set P, then, okay, maybe here, then the quasi-lambda neighborhood, lambda quasi-neighborhood is defined as follows. It is just almost the same like here, but all half spaces are shifted by lambda x from RD such that this scalar product is at most Bj plus lambda. Again, for some, okay. So what do we have in the picture? For example, if we have our P is this polyhedral set, actually polytope here, then what is P lambda? Then we shift each of half spaces by lambda. So it is quasi-neighborhood of this guy. And the real lambda neighborhood, actually it always contained in this neighborhood. Oh, sorry, because here we have upper index, here it's better to put lower index. And we always have this inclusion. The real neighborhood is a subset of the quasi-lambda hood. On the picture, the real neighborhood is the following one. Of course, it always inside this quasi-neighborhood. It's very easy to observe. Okay, so we always have this. And having defined this setup, the definition given by Zaitsev is actually equivalent to the following. It can be rewritten in the form closer to the form of the Prokhorov-Levy metric. It is infimum of all lambda such that probability that psi lies in some polyhedral set P is at most the probability that psi prime lies in the quasi-neighborhood of P plus lambda. So this summation, it corresponds to the shifting of the half spaces. And in the definition of Zaitsev, all of our subspaces are of this form. So we need to put here, okay, the same vice versa, and we need to put here for any P from our class P star, which is of this form, P star. So it is the equivalent form of the definition due to Zaitsev, which uses these polyhedral sets of this shape with half spaces, with boundaries of the half spaces parallel to coordinate planes. And having this reformulation, now it is very easy to suggest the coordinate-free definition. Because here, as I said, this P star is a subclass of PD, and more generally PM. It is just the class of all polyhedral sets which are induced by at most M hyperplanes. So if we put here not just P star, with parallel to coordinate planes, and put here arbitrary P is from arbitrary PM, and here we put, it is another object, so here we put another symbol. We denote it by LM of xi prime. We have another definition, and now it is coordinate free. And for example, if we put m equals d here, then as I said, P star is in PD, and then this definition is a stronger version of Zaitsev definition, and also coordinate free. And what we managed to prove for this definition, which is coordinate free, it is almost the same two theorems. Actually, it is almost the same theorem, inequality star. But here, of course, sorry, I forgot to say, in the result of Zaitsev, the constant, of course, depends on D, on dimension, because it is absolute constant in the one-dimensional case, and in D-dimensional case, the constant, of course, depends on dimension D. But if we consider this metric LM, then we have the following inequality. We have the same inequality, but here the constant depends, of course, on M. But surprisingly, it does not depend on D. Actually, although the result is D-dimensional, if we consider this class of polytopes which are induced by at most M half spaces, then the constant actually does not depend on D. It depends only on M. And once again, if we put here M equals D, then we recover a stronger version of Zaitsev result, coordinate-free version, and of course then tautologically it would be CD, which of course depends on D. And it is concerning the Levy metric. And concerning, also we proved the second theorem concerning the Prokhorov metric, because in this formulation, everything is all right with Prokhorov-Levy metric because it is already coordinate-free and the definition is very natural. But let us imagine for the moment that in our new definition of the Levy metric, we considered not all the Borel sets, but consider only the polyhedral sets from PM. And also we considered the quasi-neighborhood. Here we considered the original neighborhood and considered all Borel sets. And so there is also something in the middle. If we considered all Borel sets and considered a quasi-neighborhoods. And in this situation, it turned out that we can improve this inequality. So in this, if we considered not the real neighborhood, but considered the quasi-neighborhood, then we obtained the right-hand side without this term. And it is our second result. And I think maybe it's time to finish. Thank you for your attention.
So, thank you, Dima. Other questions or remarks? Yeah.
Inequalities, tau is fixed.
Yeah, it is for any fixed tau. For any.
Okay.
Yeah, thank you for the question. I forgot to say. Yes, Friedrich is over there.
Yeah.
So maybe just to clarify. So several times you told about so-called high-dimensional situation. Okay, usually high-dimensional situation means that D and N are in some sense connected, and if D is much larger than N, then your results are beautiful. But as I understood, or maybe I am wrong.
Actually, not high dimensional, higher dimension. I mean, not high dimension, which, okay, you consider symptotic when dimension goes to infinity. No, it's not the case, I consider. Just, I mean, higher dimension, it means that D is greater than 1, but fixed.
Okay.
D is fixed.
Okay. No, but it's also possible to understand what you said, not now, but during your talk, that star inequality is dimensional free.
Sorry, what is that?
Dimensional free. Free dimensional.
No, this one.
Yes.
This one,
this
yes,
one.
because it does not depend on D. Yeah.
Yes. Okay.
Further questions or remarks? Yes?
As I understand, the main motivation for the new definition is this coordinate-free property. But could you give us an example where this property is crucial and you could not use just old Levy metric?
For example, if you rotate something, then it breaks. No?
Okay, I will ask you at the coffee break.
Okay, further questions or remarks? Well, if that's not the case, then let's thank our speaker.